It's Petey the Polygon Plantain here to talk to you about some rhombi and squares.
First vocabulary term is a rhombus. That's a parallelogram with all four sides congruent. So down here we have a quadrilateral ABCD, and we are saying that it's a rhombus. Now because it's a rhombus, it's also a parallelogram, which means that all the parallelogram properties still apply. The opposite sides are parallel, the opposite sides are congruent, opposite angles are congruent, consecutive angles are supplementary, and the diagonals bisect each other. All of that is still true in a rhombus because a rhombus is a parallelogram. The only difference is that it's a specific type of parallelogram. It's a parallelogram where all four sides are exactly the same. All four sides are congruent. A square is a parallelogram with four congruent sides and four right angles. So a square, down here you can see quadrilateral EFGH is a parallelogram first and foremost. That means that, again, all of the parallelogram properties apply. It's also a parallelogram with four congruent sides, meaning that this is also a rhombus. And because it's a rhombus that has four right angles, we can also call it a square. So a square is technically a parallelogram, it's technically a rhombus, and we'll talk about this later on, but it's also technically a rectangle because a rectangle is just a parallelogram where both pairs of opposite sides are congruent and each angle is a right angle. Now, the first rhombus theorem we're going to talk about today says if a parallelogram is a rhombus, then its diagonals are perpendicular. So we have a parallelogram down here, ABCD, and we also know it's a rhombus. Because of that, we know that the diagonals, segment AC or CA, and segment DB or DB, must be perpendicular to each other. The second rhombus theorem says if the diagonals of a parallelogram are perpendicular, then the parallelogram is a rhombus. So this is just the converse of the first one. If we know that it's a parallelogram where the diagonals are perpendicular, the parallelogram must be a rhombus. Now, the third rhombus theorem says if a parallelogram is a rhombus, then each diagonal bisects a pair of opposite angles. So, down here we have parallelogram ABCD, and we know parallelogram ABCD is a rhombus. Because it's a rhombus, the diagonals are going to bisect the given angles. So, if we're looking at angle DAB right here, angle DAB is bisected by the diagonal segment AC. That makes angle 1 and angle 2 congruent to each other. Angle ABC over here is bisected by the diagonal segment BD, and that makes angle 3 and angle 4 congruent to each other. Angle BCD is bisected by the diagonal segment AC. That makes angle 5 and angle 6 congruent to each other. And same thing with angle CDA. It's bisected by the diagonal segment BD. That makes angle 7 and angle 8 congruent to each other. Again, we know this because parallelogram ABCD is a rhombus. Now, the fourth rhombus theorem says if one diagonal of a parallelogram bisects a pair of opposite angles, then the parallelogram is a rhombus. So if we know that ABCD down here is a parallelogram, and we know that diagonal AC or segment AC bisects this angle up here so that angle 1 and angle 2 are congruent, and it bisects this angle down here so that angle 6 and angle 5 are congruent, then we can say that parallelogram ABCD is a rhombus. Similarly, if we look at this angle over here, if we know that segment BD or diagonal BD bisects this angle so that angle 3 is congruent to angle 4, and we know it bisects this angle down here so that angle 7 is congruent to angle 8, then we can say parallelogram ABCD is a rhombus. The fifth rhombus theorem says if one pair of consecutive sides of a parallelogram is congruent, the parallelogram is a rhombus. Down here we have parallelogram ABCD. If we know that one pair of consecutive sides, so segment AB or BA and segment BC or CB, if we know that those two sides, they're consecutive, they share a vertex, if they are congruent to each other, then we know this must be a rhombus. And it makes sense, right? Because in a parallelogram, both pairs of opposite sides have to be congruent. So if these two are congruent to each other, then these two have to be congruent to each other, and these two have to be congruent to each other, so they're all congruent to each other, meaning that it's a parallelogram with four congruent sides, therefore it's a rhombus. The next rhombus theorem says if a quadrilateral is both a rectangle and a rhombus, then it's a square. Now this makes sense. We talked about this earlier. If we have a quadrilateral, let's say EFGH, a rectangle is a parallelogram with 4 right angles. So that's what we have here. A rhombus is a parallelogram where all 4 sides are congruent. So if we have all 4 angles right and all 4 sides congruent, then it forms a square. So a square is both a rectangle and a rhombus. You've probably heard the saying before, a square is a rectangle, but a rectangle is not always a square. A square is a rhombus, but a rhombus is not always a square.
Hope I don't split! It's example time!
Now example 1 says the diagonals of rhombus FGHJ intersect at K. Use the given information to find each measure or value. So we're given the measure of angle FJH, so angle FJH would be this angle right here, that's 82 degrees. And we want to find the measure of angle KHJ, so angle KHJ would be this angle right here. So we need to set up an equation. How do we figure out what this angle is right here? Well, I know this is a rhombus. And because I know this is a rhombus, I know that the diagonals bisect the given angles. So this diagonal right here, segment FH or HF, is going to bisect angle GHJ. So this angle has to be congruent to this angle right here. Now, how am I going to set up an equation based on what I'm given here? Well, I know because FGHJ is a rhombus, it means it's also a parallelogram. And we know that consecutive angles in a parallelogram must be supplementary. So what I can do is I can set up an equation where the measure of angle GHJ plus the measure of angle FJH have to add together to equal 180 degrees. And since I already know the measure of angle FJH, I can plug that in, subtract that out, and I would get the measure of angle GHJ. Now, because FGHJ is a rhombus, this diagonal bisects this angle, so if I know what the measure of angle GHJ is, I can just divide it by 2 to get the measure of angle KHJ. So that's what I'm going to do. So first, we need to figure out what the measure of angle GHJ is. And we said, because this is a parallelogram, that consecutive angles must be supplementary. So the measure of angle FJH plus the measure of angle GHJ have to add together to equal 180 degrees. We know the measure of angle FJH is 82 degrees, so I can plug that in here. I can subtract that out on both sides, and I get that the measure of angle GHJ is 98 degrees. Because I know that's 98 degrees, all I have to do to figure out the measure of angle KHJ is just divide it by 2, because the diagonals of a rhombus bisect the given angles. So what we can do then is take that 98 degrees, plug it in here, divide it by 2, or multiply it by half, and we get that the measure of angle KHJ is 49 degrees.
Petey says, time for a U-try!
Okay, so we are again given a rhombus. This time it's LMNO. The diagonals intersect at point P. We are given that the measure of segment LM up here is x plus 9, so we label that. The measure of angle MN over here is 5x minus 2, so we label that. We want to find the measure of MN. So the measure of segment MN over here, in order to find that, we clearly just have to figure out what x is. So how do we set up an equation here? Well, if I know this is a rhombus, I know that a rhombus is a parallelogram where all 4 sides are congruent to each other. And if I know that all 4 sides are congruent to each other, I know that segment LM has to be congruent to segment MN, which means that their measures must be equal to each other. So I can just take the measure of segment LM, which is x plus 9, plug it in here, and then the measure of segment MN, which is 5x minus 2, and plug it in here. I can then solve for x by subtracting x on both sides, adding 2 to both sides, and then dividing both sides by 4. I get x is equal to 2.75. Now, I'm not done. I want to find the measure of segment MN. So the measure of segment MN we know is 5x minus 2. So I take what I found x to be, 2.75. I plug it in for x here, and I simplify. 5 times 2.75 is going to give me 13.75. Subtract 2, and I get 11.75. Example 2 says parallelogram ABCD is a rhombus if the measure of segment EB is 12, the measure of segment AB is 15, and the measure of angle ABD is 24.9 degrees. Find the measure of segment AE and the measure of angle ADC. So first thing we want to do is we are given a bunch of different measurements, so we're going to label that on our figure over here. The measure of segment EB is 12, the measure of segment AB up here is 15, and the measure of angle ABD would be this angle in here, that is 24.9 degrees. So first we want to find the measure of segment AE. So how do we find the measure of segment AE? Well, we are given that this parallelogram ABCD is a rhombus. Now what do we know about the diagonals of a rhombus? We know that they bisect the given angles over here, and that they are perpendicular to each other. So we have a right triangle here, ABE. So triangle ABE, if that's a right triangle, how do we find the missing side of a right triangle? We use the Pythagorean theorem. So in order to use the Pythagorean theorem, all we do is we go a squared plus b squared is equal to c squared. The a and the b have to be your two legs. The c has to be your hypotenuse. So that would be the side opposite the 90-degree angle. That would be the 15 here. So we're going to go segment AE squared plus 12 squared is equal to 15 squared. That's the only one that has to be where it is. C has to be 15 because that's your hypotenuse. Now let's solve for the measure of segment AE. If I square the 12, I get 144. If I square the 15, I get 225. I subtract 144 on both sides, square root both sides, and I get the measure of segment AE is equal to 9. Next, I also need to find the measure of angle ADC. So angle ADC would be this whole angle down here. Well, I know that this is a parallelogram first and foremost. So opposite angles must be congruent to each other. So angle ADC down here has to be congruent to angle ABC up here. Well, I also know that this is a rhombus, right? And because it's a rhombus, the diagonals bisect both pairs of opposite angles, meaning that this diagonal bisects angle ABC up here. So 24.9 degrees is just half of this whole angle, which means we know this angle right here also has to be 24.9 degrees. And again, because opposite sides are congruent and the diagonals bisect both pair of opposite sides, we know each of these also has to be 24.9 degrees, meaning that if we want to find the measure of angle ADC, all we have to do is just add up both of these, or just say that the measure of angle ADC is equal to the measure of angle ABC up here, which is equal to 2 times 24.9, which is 49.8 degrees.
You turn!
We are again given a parallelogram ABCD that is a rhombus. We want to first label our figure with what we're given. We're given that the measure of segment EB is 5. The measure of segment AB up here is 13. The measure of angle BDC would be this angle right here. That's 4x minus 3 degrees. And the measure of angle CAB would be this angle right here. That's x plus 31 degrees. Now I need to find the measure of segment CE and the measure of angle BDC. So let's first find the measure of segment CE. So how do we find the measure of segment CE right here? Well, remember last time we used the Pythagorean theorem. Can we do that again? Well, I want to find the measure of segment CE. I know the measure of segment EB is 5, and I know that these diagonals are perpendicular to one another. So this is a 90-degree angle. I just don't know the measure of segment BC. Well, I do know that because this is a rhombus, the diagonals are perpendicular, like we said, and all of the sides are congruent. So if the measure of segment AB is 13, the measure of segment BC also has to be 13. Now I have created a right triangle that only has one missing side length, the measure of segment CE, what I'm trying to find. So I set up my Pythagorean theorem, a squared plus b squared equals c squared. Again, 13 is your hypotenuse. It's the side that's opposite your 90-degree angle. It has to be your c. So a squared plus b squared equals c squared looks like the measure of segment CE squared plus 5 squared equals 13 squared. 5 squared is 25, 13 squared is 169. We subtract 25 on both sides. We square root both sides, and we get that the measure of segment CE has to equal 12. Now we need to find the measure of angle BDC. That would be this angle right here. So I just have to figure out what x is first. How do I find x? Well, I need to set up an equation that involves x. Well, I'm also given this angle up here. Can I get these related somehow? Well, I know that this is a parallelogram because it's a rhombus, right? So if these two lines are parallel, cut by a transversal, segment AC are diagonal, then these angles right here, angle BAC and angle DCA, they would be alternate interior angles. So they would be congruent by the alternate interior angles theorem. You could also say that because it's a rhombus, both pair of opposite sides are bisected. So this is x plus 31, this is x plus 31, this is x plus 31, and this is x plus 31. We now know that this angle is 4x minus 3, this angle is x plus 31. What's this angle? Well, we know that these are vertical angles, so this would also be a 90-degree angle, meaning that this triangle right here, I could then use the triangle angle sum theorem and say 90 degrees plus this angle has to equal 180 because the sum of the interior angles of a triangle has to equal 180 degrees. Now I can solve for x. So let's combine like terms. 4x plus x gives me 5x. Negative 3 plus 90 plus 31 gives you 118. We then subtract 118 on both sides. Divide both sides by 5. We get x is equal to 12.4. But that's not what I'm trying to find. I'm trying to find the measure of angle BDC. Measure of angle BDC we know is 4x minus 3 degrees. So we take that 12.4, plug it in for x, multiply it by 4, and we get that the measure of angle BDC is 46.6 degrees. Now let's quickly talk about how you determine if a parallelogram graphed on the coordinate plane is a rhombus, a rectangle, or a square. So you'll be given a set of vertices. You'll be given 4 points, and they will create a parallelogram. You will then be tasked to determine if that parallelogram is a rhombus, a rectangle, or a square. To do that, you will complete 2 steps. The first would be to find the length of each diagonal, and to do that, you'll use the distance formula. If the diagonals of the parallelogram are congruent, then it's either a rectangle or a square, because those are the 2 parallelograms that have congruent diagonals. As you can see, one diagonal of the rhombus is shorter than the other. After you find the length of each diagonal, you move on to step 2, which is to find the slope of each diagonal. If the diagonals of the parallelogram are perpendicular, then it's either a rhombus or a square, because those are the 2 parallelograms that have perpendicular diagonals. The rectangle does not have perpendicular diagonals. If you know that the diagonals are congruent, the length of each diagonal is the same, and you know that the slope of the diagonals are perpendicular, then it must be a square. A square is going to have both congruent diagonals and perpendicular diagonals. If it only has perpendicular diagonals but not congruent diagonals, then it's a rhombus. If it only has congruent diagonals but not perpendicular diagonals, then it's a rectangle. Now let's do a couple examples to show you how this works. Example 3 says determine whether parallelogram JKLM with vertices JKLM is a rhombus, rectangle, or a square. List all that apply. So here, we know that JKLM, those are the vertices, so we're going to graph those. Point J is at -7, -2. We go over -7 on the x-axis, down -2 on the y-axis, put a point. K is at 0, 4. We go over 0 on the x-axis, up 4 on the y-axis, put a point. L is at 9, 2. We go over 9 on the x-axis, up 2 on the y-axis, put a point. M is at 2, -4. We go over 2 on the x-axis, down -4 on the y-axis, put a point. There is my parallelogram, JKLM. You can kind of already guess what it's going to be, but we need to make sure. So the first thing we're going to do is we're going to find the length of each diagonal. So how do we find the measure of our given diagonals? We need to use the distance formula. So let's first find the distance between points J and L. To do that, we use the distance formula, and we choose one of our points to be x sub 1, y sub 1, the other one to be x sub 2, y sub 2. We plug in the coordinates to their corresponding spots in the distance formula, and we simplify. 9 minus -7 is the same thing as 9 plus 7, and 2 minus -2 is the same thing as 2 plus 2. 16 squared is 256, 4 squared is 16. Add those together, you get 272. Now the square root of 272, we're not going to leave it like that. We're going to simplify it. The square root of 272, we break up into 2 radicals that multiply together to make rad 272. One of the numbers has to be a perfect square. That helps us simplify it. So what perfect square goes into 272? Well, a couple do. One of them is 16. So if I make this rad 16 times rad 17, I can then simplify the rad 16 because it's a perfect square. That's why we did it. Square root of 16 we know is 4, and rad 17 is a prime number, so it just stays rad 17. We then write our distance between points J and L as 4 rad 17 units. Now let's check to make sure KM is the same thing. If it is, then we know it's either a rectangle or a square. If it's not, then it's probably going to be a rhombus. So let's check. We pick one of our points to be x sub 1, y sub 1, the other one to be x sub 2, y sub 2. Plug in the coordinates to their corresponding spots in the distance formula, and we simplify. 2 minus 0 is going to give you 2. -4 minus 4 makes it more negative. It's going to be -8. 2 squared is 4. -8 squared is 64. We then add those together. We get rad 68. Now the square root of 68, we break up into 2 separate radicals that multiply together to make rad 68, one of which has to be a perfect square. So what perfect square goes in 68? That would be 4. So 4 times 17 gives you 68. Now, why did we pick 4? It's a perfect square, so the square root of 4 we know is 2. Rad 17 we said is a prime number, so that stays under the radical, and we get that the measure of segment KM is 2 rad 17 units. That means that the diagonals are not congruent to each other. They have different measures. So because the diagonals have different measures, they're not congruent, we know that the parallelogram here cannot be a rectangle or square. It's neither a rectangle nor a square. So let's make sure that it's a rhombus. How do we make sure it's a rhombus? We need to check the slopes of the diagonals. Remember, that was step 2. So let's find the slopes of each diagonal. First, we're going to find the slope of segment JL here. To find the slope of segment JL, we use the slope formula. We're going to pick one of our points to be x sub 1, y sub 1, the other one to be x sub 2, y sub 2. We plug the coordinates into their corresponding spot in the slope formula, and we simplify. 2 minus -2 is the same thing as 2 plus 2, and 9 minus -7 is the same thing as 9 plus 7. What is 2 plus 2? That's 4. What's 9 plus 7? That's 16. 4 over 16 simplifies to 1 over 4. Now let's find the slope of segment KM. To find the slope of segment KM, we again use the slope formula. We pick one of our points to be x sub 1, y sub 1, the other one to be x sub 2, y sub 2. Plug in the coordinates to their corresponding spot in the slope formula over here, and we simplify. -4 minus 4 makes it more negative. It's going to be -8. And then 2 minus 0 is 2. -8 over 2 simplifies to -4. Now the question is, are these slopes perpendicular slopes? Are they opposite reciprocals of each other? Well, they have different signs, and the fractions are flipped. So yes, they are opposite reciprocals, meaning that these two diagonals are perpendicular to each other. So this would be a rhombus because it has perpendicular diagonals that are not congruent.
Can't knock it till you try it. You try.
Okay, doing the same thing here. So first, we have to graph our parallelogram ABCD. Point A is at -4, comma -4. We go over -4 on the x-axis, down -4 on the y-axis, put point A. Point B is at -2, comma 2. We go over -2 on the x-axis, up 2 on the y-axis, put point B. Point C is at 4, comma 0. We go over 4 on the x-axis, up or down 0, put point C. And then D is at 2, comma -6. We go over 2 on the x-axis, down -6 on the y-axis, put point D. There is parallelogram ABCD. Ah, that's looking pretty squarey to me. Now, we have our diagonals, and we need to complete the 2 steps. We need to find the measure of each diagonal and see if they're congruent. Then we need to find the slope of each diagonal to see if they're perpendicular. So let's first find the length or measure of each diagonal. To do that, we're going to use the distance formula. So let's first find the distance between points A and C, the measure of segment AC. To do this, we choose one of our points to be x sub 1, y sub 1, the other one to be x sub 2, y sub 2. Plug in the coordinates to their corresponding spots in the distance formula and simplify. 4 minus -4 is the same thing as 4 plus 4. That's going to be 8. And then 0 minus -4 is the same thing as 0 plus 4. That's 4. 8 squared is 64. 4 squared is 16. We add those together. We get 80. Now the square root of 80, we can simplify that. We break it up into 2 radicals that multiply together to make rad 80. One of the numbers has to be a perfect square. So what perfect square goes into 80? 16 would be the biggest one. So we choose rad 16 times rad 5. That equals rad 80. We choose 16 because it's a perfect square. Square root of 16 we know is 4. Rad 5 stays rad 5. So the measure of segment AC is 4 rad 5 units. Now let's check the measure of segment BD, the other diagonal. So we choose one of our points to be x sub 1, y sub 1, the other one to be x sub 2, y sub 2. Plug in the coordinates to their corresponding spot in the distance formula over here, and we simplify. 2 minus -2 is the same thing as 2 plus 2. That's 4. -6 minus 2 makes it more negative. That's going to be -8. 4 squared is 16. -8 squared is 64. Add those together, you get rad 80 again. So you could stop right here, or you could just get some more practice in simplifying radicals. Break this up into 2 radicals. That's going to be rad 16 times rad 5, like we said over here. We chose rad 16 because 16 is a perfect square, so the square root of 16 is 4. Rad 5 stays rad 5, meaning that the measure of segment BD, the other diagonal, is also 4 rad 5 units. Because the diagonals are congruent, they have the same measure, we know that this parallelogram must be either a rectangle or a square. So to determine if it's a rectangle or a square, we need to find the slope of each diagonal. If they're perpendicular, we know it's a square. If they're not, we know it's a rectangle. So let's first find the slope of segment AC. To do that, we use the slope formula, y sub 2 minus y sub 1 over x sub 2 minus x sub 1. We choose one of our points to be x sub 1, y sub 1, the other one to be x sub 2, y sub 2. Plug the coordinates into their corresponding spot in the slope formula and simplify. 0 minus -4 is the same as 0 plus 4. 4 minus -4 is the same thing as 4 plus 4. So we get 4 over 8, which simplifies to 1/2. Now let's see if the other diagonal has the opposite reciprocal slope to make it perpendicular. We again use the slope formula, pick one of the points to be x sub 1, y sub 1, the other one to be x sub 2, y sub 2. Plug in the coordinates to their corresponding spot in the slope formula, simplify, and we end up getting a slope of -2. Now, are these slopes opposite reciprocals? Yes, they have opposite signs, and they are fractions that are flipped. Therefore, these two diagonals must be perpendicular to each other. So because we know that the diagonals are not only perpendicular to each other, but they are congruent, we know that this quadrilateral ABCD must be a square, meaning that it's also a rectangle and a rhombus, because a square is both a rectangle and a rhombus. Now example 4 says given parallelogram QRST, segment QS is congruent to segment RT, and the measure of angle QPR is 90 degrees, we want to prove that QRST is a square. So the first step in a geometric proof is to mark up the figure with the given information. We're given that it's a parallelogram. That's something we're going to use later on. We're given that segment QS is congruent to segment RT. Now I'm not really going to mark that up. I just know that the diagonals are congruent to each other. It's really hard to mark that up. You could put like a big arc here and a big arc here if you wanted to. I'm not going to do that. We also know that angle QPR is 90 degrees. Now, it doesn't say it's a right angle yet. We're going to have to prove that later on, and then we can mark it up with a little right angle. So in step 2 of geometric proof, we're going to state our given. So for our first step, we write QRST is a parallelogram, segment QS is congruent to segment RT, and the measure of angle QPR is 90 degrees. The reason for that, it's given. Step 3 in a geometric proof, we need to come up with a game plan. How are we going to get from what we're given to what we're trying to prove? Well, we're trying to prove that QRST over here is a square. To do that, we have to show that it's both a rectangle and a rhombus. If a parallelogram, like we have here, is a rectangle and a rhombus, then we know it must be a square. That's one of our theorems before. So from what we're given, can we prove that this is a rectangle right off the bat? Yeah, it's a parallelogram that has congruent diagonals. Any parallelogram that has congruent diagonals is a rectangle. So we could say that this is a rectangle. We then know that the measure of angle QPR is 90 degrees, meaning that it's a right angle. So we could say that angle QPR is a right angle, meaning that segment QS and segment RT are perpendicular. And since the diagonals are perpendicular in this parallelogram, we could then say QRST is a rhombus. And then after that, because we've shown that it's a rectangle and a rhombus, we can say it's a square. Okay, that's what we're going to do. So first, we're going to say that QRST is a rectangle. And that's because if a parallelogram has congruent diagonals, then it's a rectangle. Next, we said that since the measure of angle QPR is 90 degrees, we know that angle QPR is a right angle. And that's just the definition of right angle, which says because this measure is 90 degrees, it must be a right angle. Now, because we know this is a right angle, and these two lines meet at a right angle, we know that segment QS and segment RT have to be perpendicular to each other, because that's the definition of perpendicular lines. If two lines meet at a right angle, they are perpendicular. Next, because we have shown that this parallelogram, QRST, has perpendicular diagonals, we can then say parallelogram QRST has to be a rhombus. And the reason for that is if the diagonals of a parallelogram are perpendicular, then the parallelogram must be a rhombus. Now, we've shown that QRST is a rectangle and QRST is a rhombus. Therefore, QRST must be a square. And that is because if a quadrilateral is both a rectangle and a rhombus, then it's a square. And you're done.